Okay, let's go ahead and define the notion of one-sided limits. So we want to talk about a left-hand limit and a right-hand limit. So if x is less than a, and x close to a forces f of x close to L, then we say the limit as x approaches a from the left. So the little negative sign reads from the left. The limit as x approaches a from the left of f of x is equal to L. So basically the same notion, but now it's just, we just move towards x equals a from the left. And then we can give a similar definition for a right-hand limit. If x is greater than a, and x close to a forces f of x close to L, then we will say the limit as x approaches a from the right. So now a little plus sign. The limit as x approaches a from the right of f of x is equal to L. Okay, let's go ahead and revisit that last example so we can see what left and right-hand limits mean in that situation. Okay, from our previous example, this piecewise defined function, it was negative x when x is less than 1, so it's the line y equals negative x to the left of 1, and it's the line y equals x to the right of 1. So now in this situation, the limit as x approaches 1 from the left, right? What does the function look like to the left of 1? Well, when we are to the left of 1, it is just the line y equals negative x. So if you like, this will come in handy later to do this. Instead of writing f of x, it's really just negative x. So let's go over here and look at negative x. So as x approaches 1 from the left, the function gets closer and closer to y equals negative 1. So the left-hand limit is negative 1. What's the right-hand limit? So the limit as x approaches 1 from the right, that's the limit as x approaches 1 from the right of the function x, right? Because that's the piece of the function that's to the right of 1. So now this is just x. So you look at the line y equals x. As x gets close to 1 from the right, the y value gets closer and closer to positive 1. So here the left-hand limit is negative 1. The right-hand limit is positive 1. And remember, we said that the limit does not exist because these two one-sided limits are not the same, right? We get closer and closer to two y values as x gets close to 1. So because these two limits are not the same, remember the limit as x approaches 1 does not exist. Right, so the two one-sided limits are not the same, therefore the two-sided limit does not exist. Okay, so now we've come to our first mathematical theorem, our first mathematical statement that's really important. You should memorize this because you will have to use it over and over and over again. So when does a limit exist? Exactly when does a limit exist? So this theorem tells us exactly when. Let f be a function. The limit as x approaches a of f, so the two-sided limit, the limit as x approaches a of f exists and is equal to L if and only if, so exactly when, both of the one-sided limits exist and both of them must be equal to L. So this limit will exist if and only if the two one-sided limits exist and all of the limits have to be the same in order to guarantee existence. If that's not true, then this limit, this two-sided limit, does not exist. Okay, so that's something that you want to memorize. It's very important. Okay, here's our last example using the graphical method. So we want to look at this function, f of x is equal to sine of pi over x. And this is a weird function. This is called a topologist sine curve. You can see right here when we get close to 0, the function is oscillating wildly near 0. So how do we deal with the limit as x approaches 0 of this thing? Well, probably it would be good to look at the limit from either side. So what happens as we approach 0 from the left? Do we get close to a single y value when we approach 0 from the left? So when I'm very close to 0, it looks like I'm close to any one of these y values in between -1 and 1. So we do not get close to a single y value as x gets close to 0 from the left. So this limit does not exist. So once the one-sided limit does not exist, that immediately tells us that the two-sided limit does not exist. So this immediately tells me that the limit as x approaches 0, the two-sided limit of the function, does not exist. What about the limit as x approaches 0 from the right, just for the sake of completion? Well, again, the same thing. As I approach 0 from the right, I don't get close to a single y value as x gets close to 0. I take on all of the values between -1 and 1, the closer and closer to 0 I get, right? So oscillating wildly means if I move just a tiny bit from here to here, the y value could have jumped from -1 to 1. So that's too much. That's too wild. So because we don't get close to a single y value as x gets close to 0, again, this one-sided limit, the right-hand limit, does not exist. So once we say that the left-hand limit does not exist, that automatically means that the limit does not exist. We didn't even really have to compute this. But if we were asked to compute the one-sided limit, the same answer holds, right? So again, the limit as x approaches 0 from the right does not exist. So again, the limit as x approaches 0, the two-sided limit does not exist, right? There are too many oscillations in this picture.